Reactance is the opposition to the flow of alternating current caused by capacitance or inductance. So resistance is DC. Reactance is AC. Okay? The unit of measure, G, what do you know? The ohm again. Symbol used in equations is Z. It's not in yellow. Don't worry about that. At least not yet. Reactance, all resistors do is convert electrical energy into heat. Whether they are in AC or a DC system, they convert it to heat. They don't care whether the current is DC or AC. Inductors and capacitors store energy. They react differently to AC than to DC voltages or currents. Response to an AC voltage or current is called reactance. And the unit of measurement is G, the ohm again. The symbol used in equations is X for reactance. Capacitive reactance decreases with increasing frequency. So as you go higher and higher and you go up from HFs up into VHF and UHF and then the microwaves, those increasing frequencies reduces capacitive reactance. Capacitors oppose a change in voltage, and they look like an open circuit at 0 hertz, which is DC. So if you run DC into a capacitor, it's an open circuit, nothing can get through there.
The opposite side of that is?
Capacitor looks like a short circuit at very high frequencies. And we use these in our antennas that are trapped to make them do things that we want them to do. Capacitor blocks DC current, resists low frequency AC, and passes high frequency AC. But that's not in yellow. It's not on the test. Capacitive reactance decreases with increasing frequency. When energy is first applied to a capacitor, the voltage is 0, and the current jumps to a large value because there's nothing in there stored, and as much as it can take is going. And as it charges, it can take less and less. And so it will drop off. And you can see that with the multimeter in line. As the capacitor charges up, the voltage climbs to the steady state value, and the current drops to 0.
So it's kind of like a jolt?
Yes.
Yeah, when you first turn on the power to it, it's just free flow. And then it starts filling up, and there's a little more resistance, a little more pressure there. And so it slows down the current, but the voltage climbs. Inductive reactance increases with increasing frequency. So reactance is AC resistance basically in AC. So with increasing frequency, it goes up. Inductors oppose a change in current. Inductors look like a short circuit at 0 DC. So inductors and capacitors at 0 hertz DC look open.
Run that by again.
Okay, I read it wrong. Yeah, duh, because it goes right in and it comes right back out.
Uh-huh.
Okay, inductor looks like an open circuit at very high frequencies. There we go.
There you go.
An inductor passes DC, resists low frequency AC, and blocks high frequency.
Essentially, it reacts exactly the opposite of a capacitor, which is to our advantage. We use that.
We use them. Okay, when energy is first applied to an inductor, the current is 0 and the voltage jumps to a large value. Kind of like the opposite of the other one, huh? Current is 0, but the voltage is high. And then as it's in there, it comes back. As the inductor charges up, the current climbs to the steady state value and the voltage drops to 0. So it's kind of the opposite. That is the opposite of the capacitor. Notice the current and voltage are reversed when compared to capacitive reactance. They definitely want you to get this. Okay. Impedance. Impedance is the opposition to current flow in an AC circuit caused by resistance, capacitive reactance, inductive reactance, or any combination thereof. So we just call it impedance. Impedance is the opposition to current flow in an AC circuit. That'll get you through the question. We'll find out when we get to the questions. Ratio of voltage to current. The inverse of impedance is admittance. No, you can't come in. Oh, come on in. Impedance, admittance. That makes sense, right? That's easy. Okay, impedance, no. Blocker, the bouncer says you can't come in. You're impeded. Admittance, hey, come on in. You're admitted. Impedance, admittance. Impedance is the ratio of voltage to current. The unit of measurement, that friendly old ohm is back. Like I said, if you can't remember and it's asking what the unit of measurement is, it's an ohm. If you can't figure it out, just put ohm, and you got a good chance of getting it right. Hey, there's that Z again. Symbol used in equations for impedance is Z, not on the test. Resonance. Condition when frequency of applied signal matches the natural frequency of a circuit. That's what resonance is. At the resonant frequency, the inductive and capacitive reactances are equal and cancel each other out, leaving a purely resistive impedance, which is our goal for an antenna. This is the condition you want. Oh, hey, there we go. That's what you want in your antenna. Resonance. Resonant circuits are used in filters, tune stages, and receivers and transmitters, antennas and traps. We'll talk about antennas and traps in depth. We'll talk about all of that later, all of these. A resonant circuit is constructed by combining an inductor with a capacitor in series or parallel, either way. Parasitic inductances and capacitances can cause a component to become self-resonant and lead to unwanted behavior. We don't want them self-resonant, but it's white. DC circuit resistance is calculated using Ohm's law. So R equals E divided by I. We covered that in depth earlier. Hopefully everybody understands the EIR and PIE stuff, right? Similarly, in an AC circuit, impedance is also calculated using Ohm's law. Z, because that's what we use for resistance in an AC system, Z, and it represents reactance, equals E divided by R. Same thing.
Z is impedance, not reactance.
Did I say reactance?
Yeah, you did.
Impedance. Impedance transformation. Since the transformer changes the voltage and current levels in an AC circuit, it also changes the impedance. Impedance is calculated from the turns ratio, NP divided by NS, primary versus N secondary, using the following formulas. Square root of Z primary divided by Z secondary times N subprimary divided by N subsecondary. Crazy, right? It's not in the test. The required turns ratio is calculated using the following formula. Turns ratio is the number of primary divided by the number secondary equals the square root of the primary divided by the secondary. G 418 and 419. Okay, let's work a problem with that turns ratio formula. What transformer turns ratio matches an antenna's 600 ohm feed point impedance to a 50 ohm coaxial cable? And it's in yellow. That tells us that they're going to ask you that. So there's the formula, turns ratio, 650. Okay, so we got the square root of 600 divided by 50. 600 divided by 50 is 12. Okay, square root of 12 is 3.4641. So it's a whole lot simpler than what it looked like a minute ago, right? 2:1, yes. Turns ratio is, you round it off, for 3.5. Note the impedance to be changed, in this case 600, can be connected to the primary or the secondary, but the turns ratios are always stated with the larger number first. All power sources have an internal impedance which limits the amount of power that can be delivered. Maximum power is delivered only when the load impedance matches the source impedance. So we want our antenna to be 50 ohms, we want our coax to be 50 ohms, because our radio is trying to put out 50 ohms. So when all those impedances match, we get the most power going out.
This leads us to the concept of what happens when it's not identical.
Maximum power is delivered only when the load impedance matches the source impedance. I don't think I've seen a test that didn't have that question.
Right.
Z source equals Z load. That's what you're after. Maximum power when it all matches up. Most modern amateur transmitting equipment is designed for 50 ohms, but we use all kinds of stuff for carrying the load. Therefore, load impedance should be 50 ohms for maximum power transfer to the load. Z load should equal 50 ohms. It's not usually the case, and antenna impedance varies from one frequency to another. It also varies with the design and the location of your antenna. A matching network is needed to transform the antenna system impedance to the 50 ohm resistive load. There's all kinds of different ones, but we have an inductor capacitor circuit or LC circuit. That's a common one. That's a tuner with the little air capacitor. There's a couple of those and an inductor, LC. Most common type is the LC circuit. You can use lengths of transmission line. I think they're always going to be of a different ohmic value. So we want 50 ohms. Let's see, we haven't covered SWR, have we?
Correct.
All right, we won't confuse them with TV cable. You can use lengths of transmission line. You can use transformers. You cannot eliminate reactance with a transformer. An impedance matching transformer at a transmitter output can be used to present the desired impedance to the transmitter and feed line. So I call them liars. They're called tuners, and they don't tune anything. What they do is your radio wants to see 50 ohms on that line. And if it's 200 ohms, that's a 4-to-1 SWR. We'll get into what SWR is. That's bad. But the radio will probably shut down if it sees that. So the tuner goes in between and says, no, we got 50 ohms, trust me. Well, on the other side of it, it's way out. But it allows your radio to put out the power. There's nothing wrong with them. I got one sitting on top of my HF radios, because, and some of them are built into the radios because they're a necessity, because everything's a compromise. But just realize they're not actually tuning that stuff. They're just lying to the radio. Okay, so a pi network is, what do we got? Let's see. I see a capacitor and an inductor. That's a tuner. It's impedance matching with a pi network, which is in yellow there. I believe it's often used in transmitter output stages to provide 50 ohm source of impedance. Now, to remember what it is, I don't get it, but
It resembles the symbol.
I'm analog, okay, and I'm linear. That don't look like a pi symbol. There's no curves to it, but that's a pi network. Wait till we get the difference between a Colpitts and a Hartley. Oh, T network. Could anybody figure out how you'd guess this was a T network? It's got two capacitors and an inductor, but I think this T thing gives it away there. I think that gives it away. T network. Most common circuit for antenna tuners are transmatches. So you got two capacitors, those air things. You twist those around to get the most noise, and then you play with the inductor until you get a little more noise. It's a transmatch. Which of the following is combined with an inductor to make a resonant circuit? An inductor and a what is a resonant circuit? Capacitor, inductor capacitor, LC. What is impedance? Opposition to AC. What is the abbreviation for kilohertz?
Delta.
Delta. What happens when inductive and capacitive reactance are equal in a series LC circuit?
Everybody knows that.
If inductive and capacitive reactance are equal,
Alpha Charlie, I think.
You're close. Remember what we said earlier about in a well-designed circuit, the capacitive reactance and the inductive reactance cancel each other, and you have pure resistance. So if they cancel each other, where does that leave you? Very low. Very low.
Oh, low.
very low, because it's all canceled.
Because that question is only about resonance.
What is reactance? Bravo is certainly not the reinforcement of it. Opposition to AC. Which of the following causes opposition to the flow of alternating current in an inductor? Am I going to let you in, or am I going to keep you out?
Oh. Wow.
Opposition is
They're pretty reluctant.
It's not C, or it's not Charlie.
Delta. I think it's Delta.
reactance. Which of the following is opposition to the flow of alternating current in a capacitor? Opposition to the flow of AC in a capacitor is? Charlie is right. Charlie's right. Reactance. Opposition to the flow of AC. How does an inductor react to AC? An inductor.
Read them carefully.
I heard a delta. As the frequency of the applied AC increases, reactance increases.
Yeah.
Yes? You all going with that? No opposition? Thumbs up. Delta. Ah, I gave you one. How does capacitor react to AC? As the frequency of the applied AC increases, the reactance increases. Is that the one we just did?
Yeah.
Yeah. No, it's not.
No, the other one.
The other one's inductor.
Okay.
Frequency of the applied AC increases, the reactance decreases in a capacitor with AC. Inductors and capacitors are a lot opposites in how they act.
And we take advantage of that at every opportunity.
It's how we make radios.
Yep.
Or something. What is the term for the inverse of impedance? Ooh.
Delta.
Admittance?
Yeah. You got it right. Trust your instinct.
Yeah.
Come in.
You're in?
Come in.
What unit is used to measure reactance? Oh, okay, now. Before we do this, if you don't know the answer, what do you guess?
Oh.
Is that the right answer in this case?
Yes.
Are you sure?
Yes.
No, but. Well, it worked this time, didn't it?
Yeah.
Okay. What letter is used to represent reactance?
Rick.
Reactance.
Or
Bravo. I say bravo.
It's one of those, huh?
Yeah.
Yeah.
Or
Reactance is X. Impedance is Z. And impedance is the mathematical averaging, essentially, of all the reactances.
You'll deal with Z more than you'll ever see X,
Yeah.
because when you get a MFJ 269 Charlie or any of them, and you're turning a knob and you're looking for your SWR and where your antenna is,
Any of the analyzers.
you can pull up Z. Yeah, or any of the other ones. Okay, what is impedance? Impedance is voltage to current. Which of the following devices can be used for impedance matching at radio frequencies? Alpha, okay. Can you use a pi network?
Yeah.
Can you use a length of transmission line? That's two possible ones, right? So now what's the answer? Delta, all of the above. What transformer turns ratio matches an antenna's 600 ohm feed point impedance to a 50 ohm coaxial cable? Now we worked this one out already, so you probably shouldn't even have to ask or think about it, but it's the square root of the primary and the secondary, right? So 600 divided by 50 is 12.
That's the square root of 12.
Square root of 12.
3.5 plus 3.46.
It's certainly not 12, is it?
0.4167.
And 144, you're going the wrong way. 3.5. Square root of 12 can't be 12. Okay, what is one reason to use an impedance matching transformer at a transmitter output? Impedance matching transformer at a transmitter output.
Bravo, I'm guessing.
I'd say that's a good hit.
I'd say that's the most correct answer up there, but it's wrong, in my opinion, because it is not presenting the desired impedance to the feed line.
I agree.
It
But that is the answer they're looking for.
But that's the one they're looking for.
So. This don't make sense though.
The problem is they add a feed line onto that.
Yeah, leave feed line off.
If they had just said to the transmitter, it would have been functionally correct.
You're just assuming you have a feed line right after it.
Right, yes,
But it does say they have a transmitter out.
right. And transmitter output is the right. What is one reason to use an impedance matching transformer at the transmitter output? So I got my transmitter, I got an impedance matching network, and then I
The
got
feed line is part of the antenna system.
they don't care what there is, they're just going to take it. That radio cares. But that's the answer. That's the one they want. Question. See, we got through it. Questions?